Alright, on to the conclusion of this presentation series, monads. Monads are involved in most high-level features that Haskell has. There are many different metaphors one can use to understand monads in Haskell. The first is applicatives on steroids. We talked about how applicatives are kind of like functors on steroids, but monads are kind of like applicatives on steroids. As far as values with context goes, we got into that in the last presentation. We talked about lists being used as non-deterministic computations, maybe being used for pass and fail applications, where maybe you're not sure if a valiant will be present or not, I/O being used for side effects, etc. All of those are instances of monads. And in the same way that we could define functors as anything that could be mapped over by using could be mapped over by a function using fmap, and the same was true for applicatives with pure and applied over, monoids can be defined as any data type that supports the bind operation. There are also functions that can be sequenced and mapped over normal functions. This sounds complex, but think about how applicatives could only be mapped over functions that took in applicatives. Monads can be mapped over normal functions. They can let functions that wouldn't usually take fancy values take fancy values. All these metaphors start to touch on what monads do, but it's important to understand them in order to start to get at what monads are in their entirety. Monads are incorporated into many of the core Haskell libraries, including, but not limited to, maybe, either, lists, I/O, list comprehension, guards, writer, do notation, reader, state, and errors. In addition, it hides a lot of the internal working and winds up modularizing the code, often cleaning it up a great deal. Haskell has begun to be used for compiling, semantics, proving programs correct, and other high-level tasks, as monads give it the power to be able to do these things neatly. Alright, now onto a few built-in monadic functions. Bind is that symbol with two arrows followed by an equal sign, and it is the most important point for talking about monads. Bind is to monads as the applied over function is to applicatives. Its input parameter must be a monad, and it maps across a function, outputting another monad. Maybe even a function that couldn't normally handle a fancy value could be used. Return, on the other hand, is pure for monads instead of for applicatives. It takes a non-monadic value, like an integer, and wraps it up and outputs it as a monad. The just function pulls the value out of a monad. It lets you look inside the box, so to speak, to see what's there. We also have something known as the then sequence, which is kind of like bind, but the value is ignored of the monad coming in. In other words, if you replace the arrows in the second with a bind, then it acts like a lambda function and ignores the parameters, which we're going to know a bit more once we get to the do notation. Here's the do notation. Haskell came up with this do notation, which is nothing but syntactic sugar for most of the stuff that we've already covered in bind. And it makes it look a lot like imperative programming, but it's really just sequences of functions applied back to back, so you can see how the evolution works. On the left-hand side, the lambda function has been broken down into multiple lines with bind, but on the right, we've done the same thing implementing the do notation, and this idea over here is the same code on the left-hand side, but on the right side, we made the code look cleaner and more efficient using do notation. The idea behind the code on the right is simple. Bind the integer 3 to x and the exclamation point string to y and print the result of concatenating x and y. So really it's the same thing, but using sequential values that all need to be monads. Just as with functors and applicatives, lists can also be monads. One of the first interesting things that most new users of Haskell learn is about list comprehension. It seems almost like magic, as Haskell is able to read lists with whatever data types you throw at it, even many different types at a time. Once you learn a bit more about monads, you realize that the idea of list comprehension is just an implementation of the do function over a list monad with different behaviors for each different type. Kind of neat how it works. But with that, this concludes our presentation on Haskell's standard classes and monads. Any questions? Comments? Anyone? Professor? All right. Well, if anyone thinks of any later, feel free to email them to prakash@drexel.edu. Thank you very much.